Hello there, Mr. Sutton here, bringing you the AP Calculus 4-1 Part 1 homework solutions on extreme values of functions. In this one, we'll focus on finding absolute mins and maxes using the candidates test without the use of a calculator.
Hello there, Mr. Sutton here, bringing you the AB Calculus 4-1 homework solutions on extreme values of functions. For this problem, we're given this g function, and we want the absolute min of this function on the interval -2 to 1. Now, since this is a continuous function, a polynomial, and it's on a closed interval, we're guaranteed that we're going to find an absolute min. We just have to go ahead and find it. So to do that, we're going to find the critical values and then test those along with the endpoints in the original function. And we have to do all this without a calculator. So for my derivative, I've got 12x squared, just using our power rule here. And then we've got 6x minus 6. And we want to figure out where this equals 0. So we can start by factoring out a 6. That leaves me with 2x squared plus x minus 1. And then to factor that out, I have a 2x and an x, and either positive or negative 1 in each parentheses. Not sure which, so I'm just going to go ahead and guess something. So let me say 2x minus 1 and x plus 1. And let's just multiply it out to make sure that actually works. So 2x times 1 is 2x. We've got a negative x. That adds up to positive x, which is what we wanted. So we're good when we multiply that back out. So this means that my critical values, or at least my x values out of this, are going to be positive 1 over 2 for that first parentheses, if we set it equal to 0 and solve, and also x equals negative 1. Now looking at my interval, are these both in the interval -2 to 1? They are. So I'm going to have to test both of these out along with my endpoints of -2 and positive 1. Let me start with -2. We have to test all of them now with this candidates test. So g of -2, let me just figure out what happens when I plug it into each term. So this first term, that's going to be -8 times 4, so -32. Next term, we've got 3 times 4, so 12. After that, this is going to be a positive 12. And we have that plus 1 at the end. So we've got, let's see here, -32 plus 12 is -20, plus another 13, that's going to come out to -7. So -7 is the number to beat for absolute min. All right, let's test out -1. Now this one's a little bit easier. So this is going to be -4 plus 3, because it's an even exponent, plus 6 plus 1. So this is -1 over there, cancels with this one. We have 6 left over, so definitely not the absolute min. Moving on to 1/2, which is kind of gross because it's a fraction, but we'll deal with it. So we've got 1/2 cubed is 1/8. 4 over that is going to be 1/2. And then we have 3 times 1/2 squared, so that's going to be 3 over 4. Minus 6 times 1/2, so -3, plus the 1 at the end. I'm going to do kind of a middle step to make sure I get this right here. So this is really 2/4 plus 3/4, which is 5/4. -3 plus a 1 is a -2. 5/4 minus 2, that's really -8/4, so -3/4 when all is said and done. So still doesn't beat out -7. And then finally, we got to plug in our other endpoint of positive 1. This one's a little bit easier to do. So we're going to have just 4 plus 3 minus 6 plus 1. So that's 7 minus 6 is 1, plus another 1 is 2. So out of all of these, -7 is the lowest number. So by the candidates test, that's going to be our absolute min, choice A. On this problem, we're doing a little bit of theory. We want to know if f is a continuous function on a closed interval from a to b, which of the following is necessarily true. And we'll just go through these and eliminate what we can. So option A, f prime exists on the open interval from a to b. Well, we don't know that for sure. Certainly, continuity is a condition for your derivative existing for differentiability, but it's not sufficient. For example, a cusp is continuous, but it's not a differentiable point. So we're not guaranteed then that f prime exists everywhere on this interval. So this is a no. All right, next one, f of x0 is a maximum of f, means that f prime of that x value gives us 0. So we're basically saying that if we have a max, then that max happens at a critical value, or a value where the derivative is 0. And again, this is not necessarily true. For one thing, the max might be happening at a cusp, in which case the derivative would be does not exist. For another thing, the max might be happening at an endpoint, which again would not guarantee that our derivative there was 0. So that's also going to be a no. On to the next one, limit as x approaches some x value, and the function of that x value basically, because if you're approaching x0 and your function is x, then you're basically approaching x0. Basically, we're saying here that the limit and the function value are the same. That's what this is saying if you translate it into English. And this is actually the definition of continuity, so this is going to be a true statement. That's what it means to be continuous. So definition of continuity, we can say yes to this one. So choice C is our best answer so far, but let's look at the others just to be super sure. This one, f prime is 0 for some value on a to b. Well, this isn't necessarily true. There are lots of continuous functions that don't have a smooth turnaround or a plateau in them. We could have a function that's always increasing or decreasing and still continuous, so that's a no. And then the last one, the graph of f prime is a straight line. Well, there's lots of continuous functions that do not have derivatives that are straight lines. For example, x cubed, that's continuous, but the derivative of that, which has an x squared in it, is a parabola, not a line. So that's also a no. So then definitely choice C. On this problem, we want to know how many critical points this f of x function has. So critical points are going to happen where your derivative, f prime, is either 0 or does not exist. Since we essentially have a polynomial here, the derivative is going to be another polynomial, so there's not going to be any places where f prime is undefined. But we still need to find places where f prime is 0. So let's find f prime in the first place. Best way to do this is by using the product rule, unless you want to expand all this craziness. So let me use my box and ribbon then. My factors are x plus 2 to the 5th, x minus 3 to the 4th, and their derivatives, using our power rule, we've got 5 times x plus 2, quantity to the 4th, and there's no tail on this one. I mean, the derivative of x plus 2 is just 1, so we don't have to write that. And over here now, derivative of this is going to be 4 times x minus 3 cubed. At this point, let's put it all together with the ribbon. So I have 5 parentheses x plus 2 to the 4th, x minus 3 to the 4th. And then we also have, let's see, this stuff. 4, we have an x plus 2 to the 5th, we have an x minus 3 cubed, all of that stuff over there. And we need to set this thing equal to 0 and solve. Now, one way to do this would be to expand this and hate your life. Another way to do this, we could try factoring a little bit more. Because if you look closely, you'll notice we do have some common factors. This x plus 2, for example, occurs in both terms. So we have to take the greatest common factor, which means the smaller exponent is going to limit us on this one. So we can take out an x plus 2 to the 4th. These both have at least that much to give. We can also take out an x minus 3 to the 3rd, because that's the smaller of the two exponents. And if we take both of those things out, let's see what's left inside. So over here, that completely gets rid of the x plus 2 to the 4th. There's only one of these x minus 3's left, so we have 5 and an x minus 3 for this first term. On this next term, we still have the 4, and we have an x plus 2 to the first power. The x minus 3 cubed just got completely taken out. Let's keep going here. So I've got these original two factors, and now simplifying a little bit inside here, I've got, let's see, a 5x and a 4x when I distribute. That's a 9x. And then 5 times negative 3 is negative 15. 4 times 2 is 8. So that's negative 7 as well for the constant in there. Now I just have to set each of these factors equal to 0 and solve. Now you don't really need to solve because they were just asking how many critical points your function has. And it definitely looks like you're going to have 1, 2, 3 unique numbers. So that would be 3 critical points. But if you wanted to know what they are, we've got negative 2, positive 3, and 7/9. So again, that's going to give us 3. For this problem, the speed of a runner in miles per hour on a straight trail is modeled by this f of m function. M is the runner's distance in miles from the start of the trail. So apparently, how far you've run plays a role in how fast you run. We want the maximum speed between miles 0 and 3. Okay, so to maximize speed, we're finding the absolute max, which means we're going to have to test out endpoints in the original function and also critical values. To find those critical values, let's take the derivative f prime of m. That's going to be just more or less a power rule. So I could distribute this 1/10, but it's really not necessary because this is going to be along for the ride no matter what we do with it. So I'm just going to leave it out there for now. And inside, I'll just use my power rule. So this is going to be negative 6m squared plus 18m minus 12. And that 7 is gone in the derivative here because that's just going to be 0 if you take the derivative. So now I need to figure out where this thing has a value of 0 or is undefined for critical values. But there's nowhere this is going to be undefined because this looks like a parabola if you graph it. So in order to solve for zeros, what I could do, since I'm not allowed to use a calculator on this one, believe it or not, is I could factor out a negative 6. That'll come out here to be negative 6 over 10 or negative 3/4. And then inside, I've got an m squared minus 3m plus 2. All that equals 0. Things that multiply to 2 and add up to negative 3, that would be 1 and 2, and both of them have to be negative. So that means that my m values, my critical values, are going to be 1 and positive 2. All right, these are both on the interval from 0 to 3, so we're going to have to test both of them. Let's go ahead and do the candidates test now. Plugging in our endpoint of 0, that's going to zero out everything inside here. And by the way, I'm using this f of m function back up here. So that zeroes out everything next to the 1/10, zeroes out the 1/10 as well. So that means that just 7 is what we get for that one. And now plugging in a few more things, we have to plug in positive 1. So that's going to be 1/10 on the outside. And we have negative 2 plus 9 is 7, minus 12 is negative 5. There we go, negative 5. Negative 5/10 is really negative 1/2. 7 plus that is going to be 7 minus 0.5, so 6.5. And that's one of the answer choices, but then again, so is 7, so we have to keep going here. Let's try f of 2 now. So let's see now. Inside, after I write that 1/10 outside the parentheses, I've got, let's see, this is going to be negative 2 times 8, so negative 16. 9 times 4 is 36. Negative 12 times 2 is negative 24. Still have that 7 hanging around out there. Inside now, this is going to be, let's see, 20 minus 24 is negative 4. So this is negative 4/10. 7 plus that is going to be 6.6. And now for the last bit here, we've got 3, the other endpoint, getting plugged in. So that's going to be 1/10. And then we have negative 2 times 27, so negative 54. 9 times 3 squared, that's 81. 12 times 3 is 36, so minus 36. And still have that plus 7. All the stuff inside here, we've got, let's see, negative 36 and negative 54. That adds up to negative 90. Plus 81 is going to be negative 9. So this is 7 minus 9/10, basically, so 6.1. Now going back to the problem, we wanted the maximum speed. So that's going to be the highest value out of all these, which was the very first one we picked, 7. So that means we're going to have choice C. For this problem, we're given this cubic function, and we want the maximum value of this thing on the interval from 0 to 6 without using a calculator. So for maximum value on a closed interval, we have to test the endpoints and any critical values that are on the interval. Let's start by getting the derivative of this to find critical values. So f prime, that's going to be 3x squared minus 12x minus 15. And we're going to set this thing equal to 0 and solve for x now. So we can start by factoring a 3 out of this. That'll be x squared minus 4x minus 5. And then if we factor this a little bit further, things that multiply to negative 5 and add up to negative 4, that would be 1 and negative 5. So that means that x equals negative 1 and positive 5 are options here. But they're not both options because they said the interval from 0 to 6. So that means we don't have to test out negative 1. Only 5 is actually on the interval from 0 to 6. So we only have 3 things to test then for our candidates test: 0, 5, and 6. F of 0, plugging in the original function, that's just going to be 0 because everything here has an x and gets zeroed out. Now let's do f of 5. So going through and seeing what that does if I plug 5 into each term, x cubed, that's going to be 125. And let's see here, this is 25 times 6, so that's going to be minus 150. And over here, 15 times 5 is 75, so we're subtracting that. Let's see what the grand total is. So 125 minus 150, that's negative 25, minus another 75 is negative 100. And let's go ahead now and plug in 6. We have to plug in the other endpoint. So 6 cubed is 216. This is going to be 6 times 6 squared, which is essentially 6 cubed, so minus 216. And then this is going to be minus, let's see, 6 times 15 is 90. These 216s cancel, so you just have negative 90 left over. Now we were looking for the max. So we have 2 negative numbers and 0. Well, 0 wins. That's the max. So the maximum value then is just going to be 0, choice A. For this problem, g is this function right here, x squared times e to the kx, and k is a constant. We want to know what k value gives g a critical point at x equals 2/3. So critical point means that our derivative is either 0 or undefined. Well, there's no way to get undefined out of this because you have a polynomial and an exponential, which are both defined everywhere. So we're basically asking what value of k gives the derivative of this thing a value of 0 when we plug in 2/3 for x. Let's start by actually getting the derivative of this, and we'll leave k in there for now. So I'm going to need the box and ribbon for this because we're doing a product rule. So we've got x squared and e to the kx as our two factors. Their derivatives are 2x, and this is going to be k e to the kx, just a little chain rule involved in there. Using the ribbon to multiply this out, we've got 2x times e to the kx plus, this will be x squared k e to the kx, or whatever order you want to write them in. I guess you could put the k out front, it doesn't really matter. Okay, so next we want to figure out when we plug in 2/3 for the x value on these, so 2 times 2/3 e to the 2/3 k, 2/3 squared k, e to the 2/3 x, or 2/3 k rather. When we plug 2/3 in for all those x values, we want to know what value of k makes this whole thing come out to 0. Because again, we're looking for a critical point when we plug in the magic k value. So in order to solve this for k, we're going to have to use a little algebra here. This was a no calculator problem. One thing I do notice is that I have a common factor or 2 in here. I definitely have a common factor of e to the 2/3 k. That's the most noticeable one that I can factor out. But I also actually have a common factor of 2/3. So just to make my life a little easier, let me take out everything I possibly can. So 2/3 e to the 2/3 k. If I take that out of here, this first term is just going to be a 2 left over. This next term, we still have a k and another one of these 2/3, but everything else is gone. And all that should still equal 0. Now this term over here, 2/3 e to the 2/3 k, because that's exponential, there's no way that's ever going to equal 0. So that's a dead end, and we don't have to really deal with it further. This next one, though, we'll set this parentheses equal to 0. And I can subtract 2 from both sides, multiply both sides by 3 halves. Negative 2 times 3 halves. The 2's cancel. That just comes out to negative 3. So that's our k value then. That's going to give us what we need here. Choice A. On this problem, we're given the absolute value of sine of x minus 1/2, and we want to know its maximum value. Now, before you go ahead doing crazy things like taking derivatives and testing candidates and all that, let's think a little bit about what this actually looks like. So sine is a function that we know bounces back and forth between -1 and +1. It never gives you anything less than -1 or anything greater than +1. If we're taking a function that does this and subtracting 1/2 from all the outputs, well, sine minus 1/2, now it's going to be at least, if we subtract 1/2 everywhere here, -3 halves. So it's going to be no lower than negative 3/2 and no higher than positive 1/2. Now let's go ahead and say we take the absolute value of the output of that function. In that case, well, the absolute value of 1/2 is just 1/2, so that's going to be the smallest value this could possibly give you back. Absolute value of negative 3/2 is positive 3/2, so that's as high as you can do for this function. So just by reasoning out this absolute value and the cyclical nature of sine, we see that the max value we can attain is 3/2. So that would be choice C. On this no calculator problem, we want to know the absolute minimum value of negative cosine of x minus sine of x on this interval here. So fastest way to do this is to look for critical values, plug those in along with the endpoints, and see what gives us the lowest value using the candidates test. So for f prime or y prime here, that's going to be sine of x minus cosine of x. And then setting that equal to 0 and solving, well, one thing I can do is add cosine of x to the other side. This is, if you've never solved this one before, this might be a little bit tough to figure out. This is one of those, once you've seen it done, you're good at it, but if you've never seen this, then prepare to be amazed. We're going to add cosine to the other side. And from here, I'm going to do something that seems kind of illegal, but is actually totally legit. I'm going to divide both sides by cosine of x. Now, normally we're not allowed to divide by things that are either variables by themselves or have variables. The only exception is if we're guaranteed that we're not dividing by 0. We are guaranteed that we're not dividing by 0. The reason we're guaranteed this is for cosine of x to be 0, that means since it equals sine of x would also have to be 0, which means these two things would have to be 0 at the same time. Now, cosine of x is the x value of an angle on the unit circle. Sine of x is the y value on the unit circle. The x and the y value can't both be 0 and still be on the unit circle. You'd be at the origin, not anywhere on the actual circle. So we're guaranteed that this can't be 0. We can divide by it. That's going to be tan of x on the left side and just 1 on the right side. And we know that tan of x has a value of 1 at, well, an infinite number of places, but pi over 4, 45 degrees in the first quadrant. And that's all we care about, because if you look at this interval here, they said 0 to pi over 2, so that is first quadrant. So there's our lone critical value for this problem. We're going to go ahead now and plug this in along with the endpoints. So let's try out y of 0 first. So that's going to be using this original function here. Cosine of 0 is 1, but this is negative, so this is negative 1. Sine of 0 is just 0, so we're subtracting 0. So grand total of negative 1. So far, that's the winner by default. Let's plug in pi over 4 now. So this is going to be negative radical 2 over 2 for that first term, minus another radical 2 over 2. So that's going to be minus, let's see here, 2 radical 2 over 2, or so just minus radical 2 when the dust settles. And this is actually a little bit more negative than negative 1, because this is more negative than the negative square root of 1. Moving on now to our last candidate, pi over 2. Well, cosine of pi over 2 is just 0. And then sine of pi over 2 is 1, so this is negative 1. So grand total of negative 1 for this. That means that our absolute min is going to be this negative radical 2. So that would be answer choice C.